Power is defined as our ability to detect a value that we know is different from our null hypothesis. This depends on a large number of things. The sample size, so the more samples we take, the more confident we are in our estimate, the easier it is to identify a difference from our null. The actual size of the difference. If something has an effect of 10, it is much easier to detect that change than if it has an effect size of 1. The alpha threshold, or how much evidence we need in order to actually identify that difference, and the population standard deviation. The more the population varies, the more the difference is going to be difficult to detect. I want you to check out a demo I wrote. I'm going to show you a few examples here in a moment. This link is also posted next to the video. Power is the probability of rejecting our null hypothesis if a particular value of the alternative hypothesis is true. You'll notice this is starting to sound a lot more like Bayesian analysis, and it gets us a little bit close. However, calculation of power is beyond the scope of this course. I don't want you to worry about doing this. I just want you to know that this idea exists and have some idea how to do it. So in our power example, I just want to show you a few things that we can look at. So here we have a case where our mean is we have a mean of a sample minus the null. So here we are saying that 0 means that the true value is actually 0, and that that's the mean we calculated in our sample. So our null hypothesis is centered around 0. These green lines represent the significance threshold. So with a threshold alpha value of 0.05, we would need to get a value of greater than about 0.89 there, or less than 0.9 in order to reject the null. If we imagine a population whose actual value is 2, we would detect that difference 99% of the time if we sample 20 individuals. However, if we were only to sample 4 individuals, you'll note that it takes a lot more evidence to convince us that our null hypothesis is false. This means that almost half of the time that we sample from the actual distribution, it's going to be between these green lines. That makes it much harder to detect. Now we can make it even harder on ourselves if we make the difference only 1. Now note here that only 17% of the time does a value calculated from this true blue distribution stay outside of the green lines and reject our null hypothesis. This can get even worse if we do things like increase the population standard deviation. Under this condition, less than 6% of the time would our values under the blue distribution, which again we're saying is the actual population value as compared to the red, which is the null, fall outside of these green lines. However, even in this dramatic situation, if we ramp our sample size way up, we can get a lot of that power back. So if we ramp the power even higher than 100, which is the cap here, we could get a much smaller distribution. Moving the standard deviation down shows us a little bit about that. Feel free to play around with these values, see if you can find something that's interesting, or at least that interests you.